Okay, so let me share the PowerPoints and we'll pick up where we left off. Good. Oh, there we go. Shepard's here. Okay, so let's do this in the proper order. Share, and then where is it? Here it is. There we go. Start the slideshow. I think this must have been, come on, there. This must have been the last slide that we looked at. Yes. So we were just finishing up Boyle's law. Now we're ready for Charles' law. Let me just back up for a second and keep these prominent in your mind. Those are the four factors that will describe a gas, at least with the laws that we're concerned with today. Pressure, volume, temperature, and moles, or amount of gas. So we've covered pressure and volume with Boyle's law. That means that temperature and moles have to be held constant. So now we're going to look at Charles' law, which is volume and temperature relationship, which means now pressure and moles have to be held constant. Okay, so let's take a look at Charles' law. Actually, that's not correct. Unless we're gonna carry through. Charles' law is volume and temperature. So there's not a specific law that we're going to attribute to someone concerning temperature and pressure. But we can infer from the other laws relationships of temperature and pressure. So set pressure aside for now. Let's concentrate on volume and temperature attributed to Charles, which is his last name, actually. He's a Frenchman, or was a Frenchman quite some time ago. Okay, so Charles' law relates volume and temperature. And the particular law that is derived by Charles is a quotient. The ratio of volume and temperature is equal to a constant. Remember, pressure and volume was equal to a constant. That was Boyle's law. Charles is the quotient. This was a product, this was a quotient. One fundamental difference between the two, when you have the product of two variables equal to a constant, you always have an inverse relationship. Because for both, for these to vary and equal a constant, if one goes up, the other has to go down. But with a quotient, if you have two variables in a quotient relationship equal to a constant, then if one of them goes up, the other one has to go up also to maintain that ratio as a constant. So this is a direct relationship, while Boyle's is an inverse relationship. Okay, so there's one version of Charles' law. This first version there is just rearrange these things and you get volume equals K times temperature. So what does that mean? Well, notice that we have y equals mx, and plus b is the y-intercept is through the origin. So b is equal to 0. So this is a linear relationship, and we can graph it as X would be here, Y would be here, and it would go like that. Your linear relationship with K as your slope. Whatever K happens to be would be the slope of that line. Now, while we're on the topic, let's say we assign temperature values. Well, actually, temperature values have to be a special unit of measure, so I better not do that until we get there. So here's Jacques Charles, 1787, whose work was actually published later, at the beginning of the 19th century, by another Frenchman, Gay-Lussac. So Charles is given credit for the work because Gay-Lussac, in his publications, credited Charles' earlier work with Gay-Lussac's results. Okay, so if we form a table of the data as Charles developed it, we find that for each experiment, we have a different temperature, which gives us a different volume. And you see the volume is gradually increasing as the temperature increases. Now notice, the first thing that pops out for me is that the y-intercept here is 1. Right? Why is that? The reason for that is the temperature scale. Because if you go less than 0, you can still have a gas in the centigrade scale, because centigrade does have negative values. So if we extend this line to the negative side, so we have negative values on the x-axis, and we continue to decrease in volume. Okay, so if we do that, let's make some room here. If we do that, and we have centigrade scale here, and that's temperature, and this is volume, and we'll just say it's liters. Then as we graph the points, they're linear, but they're only valid for inside the curve. We call it interpolation, from the smallest to the largest. This extended line in between is an interpolation. If we extrapolate, which is we go beyond the range that's set by the experiment, if we extrapolate to the negative, then I need some help. Here we go. Okay, so if we extrapolate on the negative side, we have positive values over here, negative values over here for degrees centigrade. We really don't know what's going to happen down here. You can assume that if the gas were ideal, that it would remain a gas forever, no matter what the temperature was. And that's one of the conditions for ideal behavior. But you'll notice that eventually the volume drops to 0. The gas eventually has no volume. Now, we know that's not true because gases have molecules, right? Molecules take up space. But in an ideal world, you could extrapolate this down to 0 volume, and then what would that temperature be? Well, on the centigrade scale, it's minus 273.15 degrees C. That value is also known as absolute 0. Can't get any colder than that. Now, when we do our calculations in this class, we're just going to use negative 273. We'll just drop the last two digits. It won't affect the calculations. You won't even notice it. Okay. So, but Charles didn't do this, and Gay-Lussac didn't do that. This particular line of reasoning was proposed by Lord Kelvin. Now, I'm not sure what his given name was at the time, but the Kelvin is the important part, because he said, well, okay, if we can go down here to 0 volume, then I'm going to start a new temperature scale. We're going to call it K. Not degrees K, just K. The Kelvin scale. And now the Kelvin scale starts at 0. And every temperature value on the Kelvin scale is a positive value. And that's important for our calculations, because without that, none of the rest of our reasoning where temperature is involved will work. It has to be Kelvin, or it has to be absolute, and for us, that's Kelvin. Okay, so now what does 0 degrees centigrade represent on the Kelvin scale? Oops. 273 K is 0 degrees Kelvin, 0 degrees centigrade. Okay, so there's your Kelvin scale. And when you use the Kelvin scale, then you get that's your origin. And everything else originates from there. Any gas which exhibits ideal behavior starts at 0, 0 Kelvin scale. Okay, so let's get back to the slides. So this is the animation for just what I did on the board. Well, they say 0.16. I learned at 0.15. Since we're not going to use those last two digits, it doesn't matter. Okay, so whenever you solve problems with any of the gas laws where temperature is involved, you have to convert temperature to Kelvin. So if the problem is given, if the word problem says so many degrees centigrade, and you have to use temperature in the solution of the problem, you've got to convert it to Kelvin. Okay. So remember, we have two ways of expressing our laws. We have this, I don't know what you call it, the basic form. That's a different K. And then we have the before and after form. So for Boyle's law, remember, it was P1V1 equals P2V2. Yeah. Okay. For Charles' law, if we have volume and temperature measured at a given point in time, it's equal to that constant. If we measure it again, that same gas, which we've maintained constant pressure and volume, pressure and moles constant, but these change, then it's still equal to that constant. Okay. Which means that this one before and after is V1 T1 over V2 T2. So this is one set of conditions, the same gas at the same pressure in moles, measured at two different conditions. These quotients are equal to one another. These are actually the useful expressions of Boyle's law and Charles' law. Okay, and you can rearrange them however you need to solve for the unknown, right? Like I've said before, any equation that only has one value that's not known is solvable. Okay, so here's an example. The problem says calculate the final volume of a gas when 50 liters of gas at 25 degrees centigrade is heated to 300 degrees centigrade. So what are the before conditions? When I'm presented with a word problem like that, I like to extract the information and put it on the board in a recognizable form. So if there are variables involved, I say which variable is equal to which value. And in this case, calculate the final volume of a gas when 50 liters, starting volume, at 25 degrees centigrade, starting temperature, I stands for initial, is 25 degrees centigrade. And then it is heated, so this is the after condition, heated to 300 degrees. So final temperature is 300 degrees C. And the question was, calculate the final volume. Right? So now you have all that information extracted in a recognizable form. But remember, degrees centigrade has to be converted to Kelvin. So you might as well, before you do anything else, just say this. So you don't make that fateful error and try to do calculations with degrees centigrade and obviously get it wrong. So I didn't write the formula up here before, but K equals degrees C plus 273. So if we were solving for temperature, let's just say what if. If this problem asks us to just solve for temperature, and your temperature value would come out in K, but all the answers in the test are in degrees centigrade, then you would take your K and subtract 273 from it. Then you would get degrees centigrade. I want to let that one rest for a minute. Okay, so now that we've got everything set up, and here we've changed our temperatures to Kelvin, then we rearrange the formula so it has final volume as the answer. You can do it that way, or you can write the formula before and after, fill in the values, and solve for the unknown. Either way is fine. Then this solution gives us 96 liters. And then I always like to go back and say, is that a reasonable value? So we look at, if we start at 50 and go from 25 to 300, is the volume greater than? It should increase, right? So yes, it did increase. But the ratio, if we were to rewrite this equation this way, V1 over T1 equals V2 over T2, and write it with volumes on one side and temperature on the other, let's see, this one goes over here, this one goes over here. What's wrong with me today? There. Then you see that the ratio of the volumes before and after is equal to the ratio of the temperatures before and after. But if you ratio 25 to 300, so if we flipped it, it'd be easier to understand. 300 divided by 25 is what? That's 16, right? I think. 16 times. But the volume is not 16 times greater. The reason for that is you ratioed the wrong units. If you ratio 573 to 298, then it's a little less than twice the size. So here we go from 50 to, where is it? Disappeared. There it is, 96. It's almost twice. So that ratio is accurate. Ratioing the Kelvin temperatures will give you an estimate of what you should expect ratioed for the volumes. That's why it's so important to change those temperatures, because the ratio of centigrade doesn't work. Okay. So here's another one, but I don't want to get bogged down in doing these problems. At this point, we're going to have time to review on Thursday, and you've got plenty of these types of problems in your review document to give you practice. So I'm going to skip through this one and let's see, go to Avogadro's law now. So we had Boyle's law, Charles' law. Now Avogadro's law relates volume and moles, these two. So that means pressure and temperature have to be held constant. Now we didn't say how with Charles' law, if you've got to hold pressure and moles constant, how did he do that? Well, my guess is, and this would be a simple way to do it, is once you trap the gas and there's no way in or out, then this is constant. So you've got a container here with a piston in it. So once you set that piston in there, then the amount of gas in there is constant. So that's moles constant. How about pressure? Well, the easiest way to maintain pressure is just to put the same mass on top of that piston and leave it there. Like say 10 kilograms, you know, and it's the same force on that gas no matter what the piston does. So that's pressure and moles. Now, of course, that's force, and pressure is force per unit area. So you can't change the area of the piston either. But if the piston stays constant area and you have a constant force, then the pressure is constant. Now let's go to Avogadro. Avogadro now is relating volume and moles, these two. So pressure and temperature are constant, and we allow volume and moles to be our variables. And they are also directly related. So if you increase the number of moles, you get an increase in volume, as long as the pressure and temperature are constant. Now you do the pressure the same way, right, with a movable piston, but you have a weight on it. And then temperature, you just need some sort of a temperature bath, something that is easily maintained at a given temperature. So you could submerge your device in ice water, or you could conduct the experiment in a cave where the temperature doesn't vary half a degree the whole year round. And that would be fairly simple to do for the French or the Italians, for that matter, because they were big on wine and they stored all their wine in caves and so forth. So there's Avogadro's law. Now, Avogadro's law was developed a little bit later. Oh, and by the way, notice that there's almost a century between Boyle's law and Charles' law. Boyle's law dealt with pressure volume. Why? Because they had the instruments to do it. Volume was easy to measure. Pressure was easy to measure after the barometer was invented. But it wasn't for almost a century later till they had a reliable measure of temperature with the mercury thermometer and a system, a unit of measure that was agreed upon by everyone, right? Because by that time, Charles came along and the centigrade was accepted by all the scientific community. The zero value was freezing point of water, and 100 degrees was the boiling point. Right? So you could calibrate your thermometers very easily. Now, along comes Avogadro. Avogadro's law was fortunate when it came along. And I get the feeling I've given you this discussion before, but in the Avogadro first postulated this relationship of volume and moles at the beginning of the 19th century, but it really wasn't accepted widely and used until into the second half of the 19th century. The problem was that the chemical industry in Europe, particularly Germany, was advancing, and money, lots of money was being invested in this industry. And there were universities were doing research to support the industry. The problem was, all too often, a chemical reaction that the chemists thought they understood would go wrong. And they couldn't figure out why. Because at that time, the only way that they had to measure things, measure quantities, the stoichiometry of a reaction, was in terms of mass. And we have already learned that when you do the stoichiometry calculations, you can't calculate based on mass. You have to calculate based on numbers of atoms and molecules, on moles. But they didn't know that at this time. So they got together with this, put all their brains together at the university in Karlsruhe, Austria, in Bavaria. And they came together for, I don't know how long it was, several days at least. And at the end, they just threw up their hands. Nobody could figure it out. Nobody had any good ideas. They couldn't come to a consensus. So they just walked out. Well, at the door was a young chemist by the name of Cannizzaro. I think that's spelled correctly. He had a research paper that he was handing out reprints to everybody as they were leaving. And his work was all based upon Avogadro's relationships, volume and moles. And they politely took the reprint, and some of them read it when they got back to their respective towns and universities. And the light bulbs started going on all over Europe. The problem was solved. And here's the application of Avogadro's law. What Avogadro said was, if you have a volume of a gas, any gas, doesn't make, it matters not what gas, and you have another volume, could be a different gas, doesn't matter, as long as volume 1 is equal to volume 2, and you have both of these volumes at the same temperature, okay, and both of them at the same pressure, right? Have all those terms equal for these two gases, then the contents, the moles of those two containers have to be equal. Now, how did that solve problems? Well, if you have a different gas in each one, and this gas weighs 10 grams, but this gas weighs 20 grams, then if you have the same number of molecules in both sides, this gas, each molecule is twice as massive as every molecule in this one. So now you got a handle on numbers. And from then on, the chemical industry in Europe just exploded because they were able to solve problems. When they occurred, they knew how to fix them. And that's all thanks to Avogadro. And Cannizzaro for his persistence. See, he was a young chemist. And one thing about young scientists is most people don't pay any attention to them because they haven't made a name for themselves. But Cannizzaro quickly became recognizable, and Avogadro, he insisted, Avogadro got the credit for the relationship that he was using. Okay, so there's our relationship between before and after, initial volume, initial moles. The volume changes if the number of moles change. All right, so you can do that either by injecting more moles of gas into the container, as long as you maintain the pressure and temperature constant, or a chemical reaction could take place inside the vessel that changes the number of moles. All right, so let me use my favorite. The Haberbosch process, converting atmospheric nitrogen into ammonia. We call it fixing. Nitrogen then was fixed. This is all gas, right? So if we balance the equation, we need 2 of those and we need 3 of these. All right, notice that if you put a mole of this and 3 moles of that in the container and create the conditions for them to react, then you start off with 1 plus 3 is 4 moles total. All right, 4 moles total. On this side, you get 2 moles. So what has happened? During the reaction, assuming all of it reacts, of course, you decrease the number of moles in your container from 4 to 2. So you cut the number of moles in half. What happens to the volume? Under constant pressure and temperature, the volume will also be decreased by half because they're directly related, right? If that one goes down by half, this one has to go down by half. So you can use that relationship in chemical reactions, right? You don't have to physically change the number of moles by injecting or withdrawing, but they can happen as a result of a chemical reaction. Okay. Let's see. Anything more interesting here? We're just rearranging things Solve for your unknown, whatever that happens to be. Here's an example with the Haberbosch process. In this case, we're going the other direction. The Haber direction was a synthesis, but this, the ammonia, is being decomposed. So it's just the converse, the opposite of. This is a decomposition of ammonia to nitrogen gas and hydrogen gas under constant temperature and obviously constant pressure. Okay. So they're saying here that if you started off with 35 cubic feet and the reaction goes from 2 moles to 4 moles, you should double the volume, which you do. Okay, so we've got these 3 gas laws, and for our purposes of understanding each law, we held certain variables constant, right? But in the real world, it's more likely that you'll have several things varying at the same time. So how do we deal with them? Well, all of these laws are ways of understanding how gases behave. The gases just do what they do. And we invent these laws to help us rationalize and quantify what the gases do. So with that being said, we could say this start with Boyle's law and then introduce Charles' law. Charles' law is volume temperature relationship, right? So if we say right there, we've got volume and temperature, volume and temperature. So when would this equation be Charles' law? When pressure does not change on either side, right? If pressure 1 is equal to pressure 2, then they cancel themselves out, right? So then you're left with Charles' law. So let's introduce Avogadro's law. So Avogadro's volume in moles. So volume and moles would be like this, okay? So now, when would this equation be Avogadro's law? Well, when pressure and temperature were constant. Pressures would cancel, temperatures would cancel because they're equal. And there you would have, this is called the combined gas law. And the slide goes through just what I showed you there with animations, okay? So sometimes this is extremely useful because if you have, say, 3 of these variables changing and only 1 of them constant, then what do you do with that? Well, if you're stuck with 1 of the individual laws, then you can't solve the problem. But if you use the combined law, you can solve before and after with multiple variables changing. Okay. Now, let's see. Up to this point, we've introduced our laws in terms of before and after. If you know what the conditions were before and all but 1 of the conditions after, then you can solve for that one using the combined gas law or one of the individual laws. But what if you only know the state right now? What are the conditions now? Solve the problem. Well, then you need another expression. You need the ideal gas law. So in order to use the ideal gas law, we have to assume that the gas you're dealing with is perfect, is ideal. And what do we mean by ideal? It remains a gas under all pressures and all temperatures, like we were talking about with Kelvin, right? You take the temperature all the way down to absolute zero, it's still a gas. That would be an ideal gas, a perfect ideal gas. But of course, we know that that doesn't happen. Eventually, a real gas will liquefy, and then some of them will actually turn to solid. Like carbon dioxide gas, if you compress and cool it, you can turn it into a liquid. If you compress and cool it some more, you can turn it into a solid. That's what we call dry ice. You can take nitrogen gas, compress and cool it, and take it down to a liquid. Right? And it's very heavy. It's easier to store that way, and then use it as a liquid, and then draw some off as a gas. But those are just examples. Okay. So we also have to assume that gases have a point molecular volume. What does that mean? Well, if you remember anything in math classes, you start with a point, and that point has no area, no volume. It's just a point, right? It's our representation of nothing but the point. If, however, you have something that can be measured length and width, right? You have an area. If you have something you can measure length, width, and depth, you have a volume, right? So what we're saying with point molecular volume is these gases have no volume of their own. That's an ideal gas. That's stretching things, right? Stretching credulity to believe that. But for purposes of calculations, under many physical conditions, gases behave as if they were ideal. Now, how would they behave ideally for point volume? Well, under conditions where the space between the gas molecules is huge, is several orders of magnitude bigger than the volume of the molecule itself. And then the volume of the molecule is insignificant to the volume of the gas. Under those conditions, you can treat the gas as if it were point molecular volume. We also have to say that the gases don't interact with one another. What we mean by that is when they encounter one another, they don't repel or attract chemically or physically for that matter. They're not electrostatic charged. There's no gravitational attraction. They just act like billiard balls. When they encounter one another, they just bounce off. That's what we mean by gases don't interact. The ideal gas does not interact. And of course, last but not least, they obey every gas law. That is, there's no deviation. Now, under those circumstances, ideal gases, it doesn't matter what the gas is. Carbon dioxide, hydrogen, ammonia, oxygen, nitrogen, helium, doesn't matter. If they behave ideally, a gas is a gas is a gas. Now, real gases, they do liquefy, and some solidify as you cool and compress them. They do have actual volumes, right? We can determine those volumes experimentally. And they do very often interact. In fact, the third one is related to the first one. Why do gases liquefy? Well, because they attract one another, right? When you reduce their kinetic motion to a certain point, then the attractive forces take over, and they draw them together in liquids or solids. So the gases do interact. And of course, they interact with the walls of the container. If they didn't interact with the walls of a container, then we'd have no way to measure the pressure. You poke a hole and put your valve in there and your pressure gauge, and you get 0 reading if they did not interact with the walls of the container. Okay. So under what conditions do gases, and pay close attention to this one, under what conditions do gases behave ideally? That's important to know, because ideal behavior is much, much easier to deal with, to solve problems for, than real behavior. So if the gas is under very low pressure, which means what? Low pressure means lots of distance between the molecules. You get low pressure by decreasing the volume, right? We could start with a gas in a cylinder down here at 1 atmosphere pressure. And then we could draw the piston up to, say, 4 times. 4 times its former volume. The pressure inside would now be 1/4 of an atmosphere. Right? That obeys the law. But what have we done? By the evidence for the decrease in pressure is that the molecules are now farther apart. They don't impact one another as much. They don't impact the walls of the container as much. In fact, the impacts on this area of the container are spread out over a larger area, right? Force divided by area is pressure. So we increase the area of impact, we decrease the pressure. Okay, so under low pressure, we get ideal behavior. So what does low pressure mean? Compared to what? Low pressure is actually 1 atmosphere or less. You could get several atmospheres and still be low pressure. So the term is relative. High pressure would be something like 150 to 200 atmospheres pressure. That would be high pressure. And then you start deviating from ideal behavior. How about temperature? Well, gases behave ideally under high temperature. Low pressure, high temperature. Why high temperature? For one reason, under high temperature, they're moving really fast. Right? So they don't have time to interact. The interaction times are very short. Plus, there's a lot of kinetic energy in there. High temperature means that any type of interaction that may form between molecules is overcome by the temperature of the gas. Now, what do we mean by high temperature? Room temperature, right? Relative to what? Relative to absolute 0, room temperature is very high, right? 20 degrees centigrade is 293 degrees Kelvin, which means high temperature. So under conditions of low pressure and high temperature, you get ideal behavior for most gases. Okay, so we've introduced the combined gas equation. Now we're going to introduce the ideal gas equation, because we understand what an ideal gas is now. So if we combine, go back to combining our terms for Boyle's, Charles, and Avogadro, we could say that pressure times volume equals a constant. Okay? If we introduce temperature, then we get another constant. And if we introduce moles, we get another constant. Okay, so all of these in that relationship, product quotient relationship, equal to constant. Well, we're going to call this one, just combine all of them into one constant. Now, if we know the units of measure and how these are related to one another, we can solve for what that R value is. What is that constant worth? Well, you have to pick your units, right? Because R can be almost anything depending on the units that you use. So if we say pressure in atmospheres, okay, volume in liters, temperature in Kelvin, of course, and moles. So now the R value is liter atmospheres per mole K. All we need to do is find out what's the number, right? We got the units. We need to know the number. So what's the relationship here? Well, standard temperature and pressure for a gas, temperature is 0 degrees, pressure is 1 atmosphere. So for 1 atmosphere pressure and temperature of 0 degrees centigrade, which is 273 K, right? And for 1 mole, that's the standard, 1 mole, what would be the volume? You can measure it. And we measure the volume at 22.4 liters. So for those values, 1, 273, 1, and 22.4, combine those together, you get the magnitude of this constant. And now my mind's going to go blank. So let me go back to my slides because it'll give it to us. There it is, 0.08206. Now, that number is only valid for liter atmospheres per mole K. If you have any other units in there, and many problem solutions require different value for R, then the magnitude here of this number is different. For instance, if we if we have joules per mole K, an energy unit per mole K, the value is 8.3145. And this is also equal to Pascal cubic meters per mole K. That's what the P stands for. Probably should have been PA to differentiate from pressure. That's pascals. Okay. Let's see. Well, it's interesting, of course. Emil Clapeyron was might call it polymath. He dabbled in a lot of stuff, but he came up with this concept in 1834 for the ideal gas law. Now, when you rearrange all of this, the most common expression for the ideal gas equation is pressure times volume equals moles times the gas constant times temperature. This way you've got them all on one line, all in the numerator, which is preferable in many cases. But it's like any other equation. You know what that value is as long as you pick your units correctly. Moles, Kelvin, liters, atmospheres. And that's what we're going to be using for now. We're going to be using those units of measure and this constant right here. Okay. Let's see. It can be arranged a multitude of ways, and that's all that this slide says. You can arrange it to solve for whichever one you want. Occasionally, we don't want to know individual variable values. We may want to know the ratio. You know, what is the ratio of, let's see, volume to moles? Okay, and that might give us a number, the ratio of liters to moles under these conditions. Okay, well, in this case, upside down, moles to liters. So here's a problem, and the trick is to decide what type of problem do you have when you're dealing with gases. Do you have a before and after problem, or do you have a state problem? That is, the conditions are right now, answer the question. Right? Usually, if it's a state, you'll only be given one set of numbers for each variable. One number for each variable, excuse me. So this moles, you're only given one number for moles. You're not given before and after. Or you're not even given before and asked what the after is. Right? So that's why it's helpful to take a problem and put that information on the board, equal to some variable. Then it's easier to see what type of problem it is. Is it before and after, or is it ideal gas? Okay, so here we've identified it as a state problem. Fill in the values. Notice we changed the temperature there in the formula itself. And it turns out that under those conditions, 1.018 atmospheres is the answer. Now, what do you do under if you have other units? You've got to be able to change them to the correct unit. And the units that you need, that are your target, are based upon what's the constant? Liter, atmospheres, mole K. So your variables have to be volume liters, pressure atmospheres, moles, and K for temperature. That will tell you what conversions have to be made. Liters, it's already liters. Minus 15C, add 273 because it's got to be K. 850 millimeters of mercury, it's got to be atmospheres. So what do? Divide by 760. Gives you atmospheres. Right? Then you can solve the problem. IGE means ideal gas equation. Okay, so I'm running out of time, so I want to move along here. Here's a chemical reaction that you consider in terms of the ideal gas equation. And this is a stoichiometric problem. Calculate the mass of mercury 2 oxide needed to produce 220 cubic centimeters of, which is 0.2 liters of oxygen at 25 degrees C, 298 K. These are conversions already. And at this pressure. Well, what does that mean? Well, what gases do you have in that container? Only one gas, oxygen. So if you're given the conditions, volume, pressure, temperature, and the constant R, what do you have left? Moles. So you can calculate the number of moles of oxygen that were produced in this reaction. And once you have moles, remember, you can go anywhere in your equation. So we calculate the moles from the ideal gas equation. Then you can find out how many moles of mercury 2 oxide you have and make the conversion to mass. Right? Calculate the moles of O2. That's what we're doing here. Oops. There we go. So you have that many moles of oxygen. Use your ratios, 1 oxygen for every 2 mercury 2 oxides. So for those moles, you just double them. You got the number of mercury 2 oxide moles. There's your ratio. We're going back to stoichiometry again. And this converts from moles to grams. And there you have 1.8693 grams mercury 2 oxide required to produce these conditions for that gas. We want to find out what volume was produced. Oh, what volume of mercury? All right. So we know how many moles of oxygen. We know how many moles of mercury 2 oxide. Use either one. Convert it to moles of mercury. This is liquid mercury, you know, quicksilver. Once you know the moles of that, you can find out the mass. And then once you know the mass, you can use density to convert it to volume. Right? So that's what this equation does. Convert to mass, then use density, convert to volume. It's all dimensional analysis. Like I said at the very beginning, so many problems in chemistry are solved by dimensional analysis. Okay. So what else can we do with gases? Well, there was a particularly bright Frenchman by the name of Jean-Baptiste Dumas. And he was particularly interested in gases and how they behaved. And he used what he knew about the gases. Actually, his approach was to determine the molar volume of gas, of each gas. Right? So these gases were the molar volume of the ideal gas, we've already said, is 22.4 liters per mole under standard conditions. But by this time, they were recognizing that some gases weren't ideal, right? So he wanted to use what he knew to find the molar volume of gases, and that led to determining the molecular weight, or the molar mass of gases as well. And one of our labs, in fact, the last lab that we do this semester, uses the Dumas method. I haven't produced it yet, but I will, and show you actually how that's done. Okay, middle to late 1800s, 19th century, he was active. And he actually did a huge amount of work in organic chemistry. Organic chemistry and analysis of organic compounds in conjunction with synthesis of those compounds was just getting started in the late 19th century. It was just starting to really take off. And Dumas jumped on that bandwagon because there was, you can make a name for yourself, you can make lots of money, and chemists are human. we want to live, eat, and sleep, have a roof over our head, so we go where the money is, even though we try to be true to our research background and our research truths. But what I'm saying here is that Dumas attached his name to a number of different methods, right? So when you say Dumas method, it really could be any number of methods. So the Dumas method we're interested in is the one that determines molecular mass, molar mass, molecular weight. Now, why do we want to do that? Well, remember when we had a discussion of empirical formula and molecular formulas. Right? You have something like this, will be the empirical formula. But the actual molecule was composed of this. Let's say, okay, the molecular formula was actually that. And what do you need to go from here to here? You have to know the molar mass of the gas. And you ratio the empirical mass to the molar mass to find out what that multiplier is. So, and there are a host of different ways to determine the molar mass of a compound. If the compound is a liquid at room temperature, but it's volatile. In other words, it will vaporize easily in a hot water bath or boiling water. So if its boiling point is less than 100 degrees centigrade, then you can do this method. If it's greater than 100 degrees, it's very difficult to do. You'd have to use either a hotter source or choose a different method, which is usually what we do. Okay. So, how do we determine the molar mass? Well, we combine two equations. Right? We have the ideal equation, and then we have what does the molecular weight or the molar mass represent? It's mass per unit mole. So, if we solve this equation for moles, notice that we can substitute the equivalence into the ideal equation. Right? So there you have this, right? We took that and rearranged it. Substitute that into the ideal equation. There it is, right? Inside the parentheses, this is N. There's N, moles, which is equal to mass. So a substitution is perfectly legitimate. Now we solve for the molecular weight, right? So what we need to know, we need to know the mass of the gas at a given temperature, pressure, and measured volume. And that's what the method does. Once you know all those values, then you can solve for the molar mass, molecular weight. Okay, let's see. This is just an example, right? And I'm already out of time, so I'm gonna skip over this one and let you deal with it with your review problems. And you'll also get another taste of it in the lab when we get to that point in the Dumas method. Right? You can review the slides. Use the information that you're given there in that problem and solve for the molar mass of the gas. Okay? So what we do in the lab is we have several unknown, well, I know what they are, but they're identified by some number of volatile liquids. And if you were there in person, you would just pick one of them. And you would run the experiment, and then you would take the molar mass that you determined for that one sample and look at the table of values and pick out which one it was based on its molar mass.
Is there any way we could is there any way you could schedule a Zoom meeting for the lab just so we could discuss like what's going on?
Folder credit bureaus.
Yeah, are you talking about this lab in particular, or any of the labs? We could, Thursdays, we have time set aside for lab.
Yeah,
I think
can we
that was-
start doing that?
Yeah, sure. Sure, we can Zoom, let's see. I'm not sure, I may already have set it up. If I didn't, I'll send you an email with the link. So we'll either use my personal link that I use for office hours, or I'll set up a separate link just for the lab. That's probably a better way to do it. Then you would go to Blackboard, to the Chem 103 course, and do like you do for the 101 and click on the Zoom and log in or tune in or Zoom in on that particular time and day. Okay, so I can do that on Thursday.
Okay, yeah, that would help out a lot. Now, I'm not sure if I'd be able to sit through it all, but as long as it's recorded, I'd be able to go back and watch it. But I just know that'd be helpful to me personally.
Well, it would, since I'm already doing recordings of the labs, the Thursday meeting would be an open session. I wouldn't conduct it like I was giving a lecture. So I would be there. We would solve your problems. I could do a short presentation on the theory behind the lab and that type of stuff. But it wouldn't be like a complete lecture series. It would be more like a problem-solving session.
Okay.
Yeah, we can do that. So let me make myself a note to set up Zoom for Chem 103. Right, so I'll do that, and we'll just come together voluntarily. Right? I'm not taking roll, but if you can show up on that particular time, yeah, Thursdays between 2 and 4 o'clock. And we can talk about the labs. Okay, so I'm going to take a short bathroom break and come back and finish the discussion. So if you need to be somewhere, go ahead. If not, I'll be back in a couple minutes.
Thank you.
Kitties. Okay. All right. So let me see how much more I've got to do. Yeah, we have a couple of things that really need to be covered. All right, so this is just some words of advice. If the conditions are really complex, for instance, in this case, we're calculating the final volume of some gas when 50 liters of gas at this temperature and this pressure is cooled to 25 degrees and compressed to 900. All right, so is this a state function or a before and after? It's before and after, because we're saying calculate the final volume when you're starting from this volume. And you have this temperature and you're going to that temperature. You know, this pressure and you're going to that pressure. Under those circumstances, you write down all your before and after, the initial and final conditions on the board with next to their variables. Then you decide which form of the combined equation is useful. You can write the whole combined equation and say, is anything constant? If anything's held constant, those terms drop out. Then you can plug in the ones that you know and solve for the unknown. And that's all that we're doing here. And this is just another way of expressing the combined equation, right? Because before, when we were doing before and after equations, we're saying like P times V, P1 V1 equals K. But if you change the conditions, P2 V2 is also equal to K. Well, under these conditions, PV over NT is equal to R, which is a constant. So if things become different, a different P, V, N, and T, they're still equal to R. So that means before and after. So they're related. And there I show the moles dropping out because the moles did not change. Before and after moles are constant, so they cancel out. And what are you left with? You're left with an answer. Okay. All right, so here's another problem that I'm going to skip, I believe. Yeah. The lesson for this problem is if you have a before and after problem with a combined gas law, like we're setting up here, then the only, the two conditions, three. First, find out, are there any constants? They cancel out. Second, change your temperatures to Kelvin. First, do that before you do anything else. Then, are the other units of measure equal on both sides? Right? Do you have volume in terms of liter? Do you have volume in terms of cubic feet? What's your units for pressure? If the units for volume, pressure, and moles, of course, are the same on both sides of your equation, then you don't have to change them because the ratios will cancel those units. Right? So here we go. I didn't change the cubic feet here or there because they cancel. I didn't change anything here. Actually 4 moles of gas, 2 moles of gas, millimeters of mercury. We just leave millimeters of mercury alone so that the answer will be in millimeters of mercury rather than atmospheres. When you don't have to deal with the units of measure for your constant, when it's a before and after problem, the only one that you have to change is temperature. The rest of them can be the same on both sides of the equation. And that saves you a lot of work. Just don't do that with temperature. If you try to do it with temperature, the problem is wrong from the beginning. Okay. Now we'll come to John Dalton, who we've seen before. So he did work with lots of different things. And he noticed and postulated, actually, that the pressure within a vessel for a mixture of gases is equal to the summation of the individual pressures of those gases. We call them partial pressures. So if you could measure the partial pressure of oxygen in the atmosphere, it would be about 2/10 of an atmosphere, 0.2 atmospheres. If you could measure the partial pressure of nitrogen in the atmosphere, it would be about 0.8 atmospheres. 0.8 plus 0.2 is 1. So there you have your partial pressure of nitrogen and oxygen, and I'm leaving out some minor components. But this is just to illustrate what we're talking about. So the major component has the higher pressure, and the minor components have lesser pressures. But once you add them all together, they equal the total pressure of the gas under those conditions. Right? So this is our reasoning. If we take the ideal gas equation and we parse it out, or we solve for pressure, right? So we have the total pressure is equal to the total number of moles times the gas constant times temperature divided by volume. Then we can take this term and spread it out. So this is the number of moles of one of the gases, which is also equal to gas constant times temperature times volume. This is the second gas. This is the third gas. And each one of these values, which was derived from that expression, is equal to its individual pressure for the gas. And it's all based upon the number of moles of gas that are in the container. So there's the Dalton's law expression for these three gases. And here's an alternate expression where we have factored out the number of moles. So go back up here to this equation, and R, T, and B are all the same. So they can be factored out just like you were in a math class. Factor them out, and you leave behind N1 plus N2 plus N3, which is here. And that's the total number of moles. So we have a special expression for the ratio of the number of moles of an individual gas to the total moles of gas. We call it the mole fraction, and we designate it by a big X. So the mole fraction of a gas, let's say A, is equal to the number of moles of A divided by the total. Simple. It's a fraction. The fraction of this one per total is the mole fraction. Now, under constant conditions of temperature and volume, the mole fraction of a gas is proportional to its pressure. So if we measure pressure in atmospheres, and we know the mole fraction of A, then the mole fraction times the total pressure is equal to the pressure of A. And we can also solve that for mole fraction. If we take this over here, put it down here, then we get that ratio. So the ratio of the partial pressure of A to the total pressure is also the same as the mole fraction of A in that gas. And we use that relationship very often to determine composition of a gas, say as a consequence of a reaction. Right? So here's how we would express it in terms of moles. And of course, if you are accounting for every gas in the mixture, then if you add up all the mole fractions, they have to equal to 1. So here's an example. Here's a balanced equation for, and I sort of gave it away here, the detonation of this compound into these individual gases. That compound is nitroglycerin. So this nitroglycerin in this balanced equation will produce, from 4 moles of nitroglycerin, you get 12 moles of carbon dioxide, 10 water, 6 nitrogen, and 1 oxygen. That's where the explosive force of nitroglycerin comes from, because you're almost instantly, in a fraction of a second, you're changing 4 moles into 12, 22, 28, 29 moles, going from 4 to 29 moles, like that. That's where the force of nitroglycerin comes from. Because Avogadro said, increase the number of moles, increase the pressure. So you're creating an overpressure in a confined space when your nitroglycerin decomposes. It detonates. So these conditions are given. Initial conditions. What's the pressure if you have a 100-liter vessel at this temperature and that initial pressure? Well, let's see. No, this is before and after, because there's volume, there's temperature before and after. Here's the beginning pressure. So what you want is the ratio of moles. So if we set up our combined equation, we find that the number of moles final is 29, the number of moles initial is 4, and then you have these other changes in condition, and we can find out the final pressure. Right? So here's 29 gas and 4 gas, that's moles of, and these are the other conditions that are met. And of course, when we solve this problem, we would write those conditions, those values for each of the variables up in a list so that you can put them in the right place in your equation. If you put them in the wrong place, you get the wrong answer. And the pressure would consequently be 297 millimeters of mercury. Okay. So each gas contributes its own partial pressure. If the total pressure is 297, what's the partial pressure of each one? Well, we use that ratio each to the whole, right? There's the whole, right? So the mole fraction we know is going to be, for carbon dioxide, 12 divided by 29, right? So that's the mole fraction of CO2 times the total is the partial pressure of carbon dioxide. And we do the same thing for each of the others. Just ratio their moles in the balanced equation to the total. And we find that the total pressure should be very close to 297.61. We were off by 0.02 of a millimeter. Okay, so that's Dalton's law of partial pressure. Let me see if no, I'm going straight into kinetic theory. One practical application of Dalton's law of partial pressure has to do with reactions, chemical reactions that produce gases. And we want to catch the gas that is produced in the reaction so that we can analyze it. We don't want to leave it in the vessel where the reaction took place. So we want to catch all the gas that comes out of the reaction, and we do that very often using water displacement by the gas. So if you have your reaction here, and you have a vat of water, and you have a container, say an inverted graduated cylinder, how about that? Which has been filled with water, right? So there's no gas in here now. So we catch the gas here. So it makes bubbles, right? And it's captured up here, and you can measure the volume. Well, the problem is, what are we doing? We're bubbling that gas through water, and water has been known to vaporize. So we get water vapor and the gas in there. So let's just suppose we're catching oxygen, all right, for argument's sake. We've got oxygen in here plus water vapor. So how do we tell how much of that is due to oxygen and how much is due to water? Well, fortunately, water has a very well-defined pressure slope with temperature. So all we need to know is the temperature, and we can tell what the pressure of water is in there, the partial pressure of water. So the total pressure we measure, and then subtract that, we know the total pressure. We know the partial pressure of oxygen. So that's a practical application of Dalton's law. Okay, so up to this point, we've been talking about laws, right? Laws just says, this is what happens. If these are the conditions, you always get this result. I don't know why, it just happens that way. The kinetic molecular theory of gases, and we've touched on them up to this point a little bit, but this is a formal presentation of the kinetic molecular theory of gases. And the kinetic molecular theory was developed for gases first, and then it was made applicable to liquids and solids, because many of the results that accrue from the molecular theory of gases can also be ported over to liquids and solids. But we start with gases. So we need some basic postulates, things that we have to assume, otherwise we can't proceed any further. So the basic postulates are the kinetic molecular theory, and we're using these to help us understand why gases behave the way they do. First of all, there are a huge number of particles of atoms and or molecules in a gas. They're just almost uncountable. Well, we couldn't count them one by one. We have to count them by averaging, by weighing, like we did at the very beginning of this course. But there are large numbers of particles, which means what? We can't track individual particles. We have to do it statistically. We have to base our assumptions upon group behaviors. large numbers of particles. The particles are very small. The molecules are extremely small compared to the distances between them. That's why when you put two gases together, you always get a solution, right? Because there's plenty of room for everybody. So the particle size is very small, and the distance between them is huge compared to their particle sizes, which leads us to the conclusion that they have a point molecular volume. They are also in constant, very rapid motion, high velocities, extremely high velocities. In fact, they verge on the speed of sound in many cases, depending on the temperature, of course. So, we've got a large number of particles. They're spaced very far apart, and they're moving lickety-split. They do collide, right? Even though there's lots of distance between them, they're moving so fast that they can't avoid colliding with one another. And they collide with the walls of the container. That's how we measure pressure. Now, what we have to do, because we can't count individual ones, and we can't calculate the kinetic energy of individual molecules, we take an average kinetic energy for the molecules, and that is related to temperature. In other words, as the temperature goes up, the average kinetic energy of all the molecules in that container goes up. Right, so they go together. And we have to assume that when they do encounter one another, that there are no intermolecular forces at work. That is, nothing attracting or repelling them other than the collision itself. Okay, those are the postulates for the kinetic molecular theory. Now, since we're talking about kinetic, kinetic implies motion. And even though we've made these assumptions about gas particles, each particle has a mass, which means it also has a kinetic energy. So individual molecules have a kinetic energy, which can be expressed by that equation. 1/2 mass times the velocity squared is kinetic energy. Okay. Now we're going to use large particles for our examples. We're going to use bowling balls. But let's look at the units of measure first. So what's the standard unit of measure for energy in the SI system? Joules. So there's our unit for energy. What are these standard units? Well, mass is kilograms, right? Kilograms. Velocity is meters per second. And we square that. So what that means is 1 joule is equal to a kilogram meter squared per second squared. Now, why is that important? Well, in some calculations, we need to make conversions, right? And if we just have joules in the expression, then none of the units are interconvertible. So we have to substitute this for joules sometimes. That's the only point I'm trying to make here. Okay, so let's say we have 7 balls, bowling balls, and each has its own energy. Each weighs 5 kilograms each, right? So that's about a 12-pound bowling ball, right? So if the kinetic energy of each one can be calculated. All we need is velocity, and we have mass, kilograms. So 10 squared times 5 is 500, and a half of that is 250. So there's your 250 joules. Right? So we do that for each one of these balls, and let's say they're moving at different velocities, 10, 20, 30, 40, all the way up to 70. Right? So we have these energies associated with them. So what's the average kinetic energy of all of these balls together? Well, add them together, divide by 7. Right? And that bar over V, well, this is average velocity. I'm getting ahead of myself. I want to calculate average energy. But let's say we calculate average velocity first. Right? So we take these, add them together, divide by 7. We get 40 meters per second is the average velocity. So what would be the, let's say we take the average kinetic energy now and back figure it to what velocity of a 5 kilogram ball would give us that energy. So what am I saying? Well, let's calculate the average energy first. Let's see. Here it is. So if we take all these energies, add them together, and divide by 7, we find that the average kinetic energy is 5,000 joules. So we would say 5,000 joules is equal to this, and we could substitute 5 kilograms in here. And then solve for velocity. So what would the velocity be if we did that? Okay, substituting the values. We're rearranging here first, rather than doing it this way. Each way works. So we insert the values, and here, in order to make things cancel, we can't use joules. We're going to use the equivalent of joules, kilogram meter squared per second squared. Right? So that cancels. And then the square root of meters squared per second squared is meters per second. So the velocity of a 5 kilogram ball that would give you that energy is not 40 meters per second, but 44.72 meters per second. Right? What's wrong with this problem? What's this picture? The problem is that you cannot use average velocity to express average energy. Whether it's 7 bowling balls or 10 moles of gas molecules. Say, we need a different expression. So what is this value actually? It's not the average velocity. It, in fact, derives from the, and this is a little overkill. I apologize for that. But just say, this is in the, when something is moving, a particle is moving, it can be expressed as movement in 3 dimensions, right? How fast is it moving in the x direction, right? How fast in the y direction? How fast in the z direction? X, Y, Z. That's all that we're doing here. We're doing a vector analysis of the movement of that particle. That's all we're doing here. So this 1/2 mv squared, and mu is the part of v for that particular direction. That's why we use a different symbol. Mu is the small letter mu from the Greek alphabet. So that's the energy in this direction, in the x direction, in the y direction, and in the z direction. You add them all up, and you get their total energy, right? Okay. So if we say we have this many moles of those particles, then it's sort of an averaging effect of the number of moles. And what we end up with, and we've taken a lot of intermediate steps here without explaining what they are. So you're not responsible for this expression, believe me. What I want you to focus on is the concept of the root mean square velocity. The root mean square. So what's the root mean square? It's a statistical value. And in statistics, root mean square is used to get rid of all your negative numbers when you're doing a statistical calculation. You don't want negative numbers hanging around. So what do? If you square a negative number, you always get a positive number, right? Right. Well, the problem with that is, once you got that squared number, it doesn't represent the original, right? Because it's squared. So once you've got that squared number, then you take the square root of it. And now you've still got a positive number. Right? So in physics, we use root mean square to calculate the value that's closer to the true velocity. Right? So if we take the average of the squared values, right? So what would that be? Well, let's do the first 2 or 3 of them. 10, 20, 30, say. Square this one. Right? Square that one equals 100. Square this one equals 400. Square this one equals 900. Then you take the average of those numbers, right? That's the square part of the root mean square. So we're working backwards. Root mean square. Okay, square. We did the square right here. That one. Now we take the mean of it. So what's the mean of 1400? Right. 3 into 1400 is what? I can't do that in my head. So let's say 1400 divided by 3 is 467. Right? So there's the mean. Now we're going to take the square root of it, right? Because we squared it first, we can't leave it there. That doesn't represent reality. So we're going to reduce it by taking the square of it. So there's the mean. We did the mean. Now we're going to take the root of it. So what's the root of 467? 467, square root. Where is it? Here it is. 216. All right. No, 21.6. Excuse me. 21.6. So instead of the average of this would have been what? 3 into 60 would be 20. 20 would be the arithmetic average here. But the root mean square average is 21.6. Now that, in the physical world, is reality. Okay, so that's calculating the root mean square of all of the particles in your container, the gas particles. And now we have a relationship, and the derivation of this formula is beyond this course. Let's just put it that way. The root mean square velocity of the particles in, which is sort of an average of the particles in your gas, is proportional to the square root of this expression, 3 times the gas constant, and this gas constant will probably be the one with energy, the 8.3145. And the temperature, of course, will be Kelvin. And the root mean square velocity is equal to this, and MW is molecular weight. Right? So as the molecular weight if you hold temperature constant, right, hold temperature constant, then if you increase molecular weight, the root mean square velocity has to go down, right? They're inversely proportional. That's what that expression says. Oh, there's the R value. It is the one with joules. Okay, so these are some simple calculations. Calculate the average velocity for air at 37 degrees. Now, what does that mean? I think that means the root mean square velocity for air. So if we know the molecular weight of air, and this is an average value because we know that air is nitrogen and oxygen, so we're using this 29.02. Then we substitute values in that equation, right? So it looks kind of unwieldy, but there I'm putting all the units in here so we can track them. So this is joules, kilogram meter squared per second squared, then mole K. And then here's the temperature, and there's the molecular weight in SI units, kilograms per mole. So there's one place that can trip you up. This is the molar mass that you would get off the periodic table, or you would, the same units. But when you put it in this formula, it has to be SI units, kilograms per mole, right? So you have to change it. Move the decimal place 3 to the left. Cancel our units, and we find that the root mean square velocity of air is 516 meters per second, which is what? Well, dimensional analysis is what this is. And we find that it's 1,155 miles per hour, right? That's faster than the speed of sound. So at 37 degrees centigrade, which is, by the way, what is that? Why did we pick 37? That's body temperature in centigrade. 98.6 degrees Fahrenheit, 37 degrees centigrade. So if we substitute helium in there instead of air, then we find that we've decreased the molar mass of the molecules from nitrogen and oxygen to helium, which is a lighter molecule. We find that it has to move faster to give us the same average kinetic energy represented by that temperature, right? So qualitatively, we see that the lighter molecules give us higher velocities. That's why when you breathe helium and you try to talk, the velocity of the sound waves increase and consequently increases the frequency. So you talk like Mickey Mouse. Now, here's the last one. We're going to take that relationship of molecular weight and derive, well, we won't actually derive it, but that's the origin of Graham's Law of Effusion, or it's often called Graham's Law of Diffusion. It uses the kinetic molecular theory of gases to determine the molecular weight of a gas. So what do you need? Well, you need two gases, and you need to know the molecular weight of one of them. So we're ratioing one against the other, and that's what this expression becomes, right? The velocity, in here we're not talking about volume, we're talking about velocity. But this V, I probably should have used a small v. The velocity of A ratio to the velocity of B can be multiplied by the same amount of time. So if we watch the velocity of the gases movement in a container, then over a period of time, we should see movement. And the distance that's traveled is velocity times time. Correct? Velocity is meters per second times time, cancels seconds and leaves us with meters. So that's a distance. So the distance that A moves relative to the distance that B moves is also equal to, since velocity is equal to each one of these, we're ratioing them. Ratioing this one to that one, this one for A, this one for B. Notice that 3 is the same, R is the same, T is the same. So those cancel out. And all you're left with is the ratio of the molecular weight of B to the molecular weight of A under the square root. Okay, so what that means is the distance that B travels, let's just, for argument's sake, A is light and B is heavy. So the distance that A travels is going to be greater than the distance that B travels to give us this ratio. Right, now, what does that look like practically speaking? Well, here's an example. You put two gases together in a container, and we're going to use HCl, hydrogen chloride gas, right? It's not dissolved in water, so it's a gas, hydrogen chloride, not hydrochloric acid, and ammonia. And we stuff them in the ends of a transparent tube at the same time. And the nice thing about this is when ammonia meets hydrogen chloride, they form ammonium chloride. And ammonium chloride is a solid, so it forms kind of a haze, and you can see where they meet in that tube and measure the distance that one moved relative to the other. Okay, so the distance that ammonia moves relative to a ratio to the distance that hydrogen chloride moves. Let's stop for a second. Which one's going to move farther? Hydrogen chloride at 36 grams per mole or ammonia at 17 grams per mole? We should see them meet closer to the hydrogen chloride because it hasn't moved as far, right? So that curtain, that haze should form closer to the hydrogen chloride side. And the ratio of the two is expressed here by that value. And the ratio is still equal to the square root of molecular weight of hydrogen chloride divided by the molecular weight of ammonia. So here's an equation. If we know this distance and that distance, and we say we knew hydrogen chloride, but we don't know ammonia, then you can solve for the one unknown. But for this demonstration, we're actually going to calculate what is the ratio of the two. Right? So there, 1.463. So the ratio of hydrogen chloride to ammonia is 1.463. So if X is the distance that, wait a minute, where's my, I forgot to say what X is. X is the distance that hydrogen chloride travels. Right? So if X is the distance that hydrogen chloride travels, then the total distance is the summation of both. So this one travels that distance, and ammonia travels this many times faster or farther. Right? So you add them together and you get the total. And we solve for X, and we find that the distance that HCl traveled was 60.9, and the distance that ammonia traveled is 89. So ammonia traveled farther because it's a smaller molecule. And you can use that as a way of determining the molar mass of an unknown gas. So there you can use that to convert your empirical formula to your molecular formula, because it's independently determined. And this is just what it would look like. Right? They meet in the middle somewhere, form that ammonium chloride, and there you have it. Now, practical application of HCl and ammonia. So we have a fume hood, right, with a fan, and we want to be sure that it's working. Say it's really quiet, which is unusual for fume hoods. So we put a beaker of concentrated hydrochloric acid, which fumes HCl vapors. And right next to it, we put a container of ammonia, liquid ammonia, like it's not pure ammonia, but just ammonium hydroxide solution, and it also vaporizes ammonia. They meet here, and they form a visible fog, which is swept into the unit, and you can see that it's moving. See, the air is moving in your fume hood. Okay, so we're almost finished. So in this problem, we're comparing ammonia, which we know, against a gas which we don't know. And they're allowed to diffuse toward each other at in a 120 centimeter glass tube. And after 5 minutes, we see the smoke ring form. Now, we don't know what X is. We just know that it reacts with ammonia. So we know that the distance that's traveled, smoke ring forms 87.9 centimeters from the ammonia end. So using Graham's law, we can say this ratio is the ratio of, the distance ratio is this distance for ammonia, which has moved that far, and then X, which has moved this far. Right, so that's the ratio, which is equal to the, see, because X is on the bottom here, X has to be on the top here. They're inverted. We know this value, so now we can solve for what is the molecular weight of X. Right? Just shift things around and find out that, well, we know that the reaction with ammonia is probably a halogen of some kind. And we have these to choose from. And hydrogen iodide gives us the closest approximation to identifying X. Okay, one last comment. A very practical application of Graham's Law of Diffusion was used during World War II, the Manhattan Project, and it was used to separate isotopes of uranium. Right? So the two major isotopes in uranium are 238 and 235. Right? This one is very small, a minor amount, a fraction of a percent. This is the major amount, but this is the one that fissions. This is the one that can make a weapon out of. So we need to separate this one from that one. One of the ways that it was done was to convert all of the uranium in a sample. Once you have pure uranium, but you still have the isotopes mixed, convert it to the fluoride. Now you got gases. So what do you do with those gases? Well, the molar mass of this one is slightly less than this one, which means what? It travels faster. So we just need a way to separate based on that speed and actually based on Graham's law. So what do you have? Well, you have filters, right? Filters. Stacks and stacks and stacks and stacks of them. Hundreds and hundreds of thousands of filters. And as they pass through, you become enriched in 235 each time it passes through the filter. Until at the very end of the filters, you end up with weapons grade uranium. You still have some 238, but you have enough 235 there that if you put it together in critical mass, it'll explode. So what was the problem? Well, the problem they had to solve was the corrosive nature of the fluoride. Uranium fluoride is extremely corrosive. It will eat up stainless steel in no time. Fortunately, at this time, DuPont had come up with a new material called Teflon. Teflon is resistant to this type of corrosion. So all they had to do was fabricate the Teflon in such a way that it has tiny pores in it. I mean, very small pores. And then under pressure, the 235 would be steadily enriched through every stage of the filtration. Right? So you probably have imagined by now, this operation to produce enough 235 to make a bomb needs lots of space, room. So to go from 0.72% natural abundance of 235 to sufficient quantity, see, there's just a very small amount of difference. You need lots of space. And this is where they did it. It was a plant called K25 in Oak Ridge, Tennessee. And in the late 50s, early 60s, I lived there with my family. I was just a little kid then. But they had this plant, and you could drive around it. You couldn't go in. I mean, it was high security, but it had a fence around it and a road, and it would take you about 15 or 20 minutes to drive around the place. It was that big. And most of that space is occupied with those filters. And it worked. There are other ways to do it. Now, of course, it's more efficient to use ultracentrifuges, but this worked. And it worked based on Graham's law. Okay. So this is just a recap. Ideal gases, real gases, and how do we deal with real gases? Well, for us, we don't need to bother with it. But for those who are active in chemistry and working with gases under conditions where they behave as real gases and not ideal gases, you need correction factors. And that was developed by a man by the name of van der Waals. He introduced correction factors to the real gas, the ideal gas equation, and won a Nobel Prize in physics for it. So notice that this is, here's the pressure term, here's the volume term. No, excuse me, there's the pressure term, pardon me, pressure term. Here's the volume term, and then here's moles, gas constant, and temperature. They don't have to be dealt with, just the pressure and volume. So it has this constant factor. Actually, this constant is characteristic of the gas. And then the ratio of moles to volume squared adjusts the observed pressure to the actual ideal pressure. And then you subtract moles times this other factor. So the A factor and the B factor were introduced in this arrangement so that the equation could accurately predict conditions. Okay? So those are van der Waals corrections, and you don't have to know those. I'm just illustrating the fact that we do know how to deal with real gases. It's just that for our purposes, we don't have to deal with them. Okay, Let me stop the share and see if there's any response from who's left. I've gone another hour over, which is not unusual for me. So in Blackboard, you may have already seen the last week's video I posted as part 1. This will be posted as part 2. And you can skim through the stuff that you already feel comfortable with and just go to the places where you need to drill on it. And then next Thursday, we'll do our review document problems on gases. We only have one chapter, right? So your entire focus can be on gases only.